learners, welcome to the channel Video Lectures for Engineering Students. This video is to explain the curvilinear translation of a body. Curvilinear translation. So what do you mean by curvilinear translation? Say if the points of a body or the particles of a body move along parallel paths, that type of motion is called as translation. Okay. If these parallel paths are concentric circles, then that is called as a rotatory motion or angular motion or rotation. Okay. And if both of these happen simultaneously, that means both translation and rotation happen simultaneously, then that is called as a general plane motion or combination of or combined translation and rotation. So if a body is moving along a curve, and if all the particles of the body are moving along parallel curved lines or paths, then that type of motion is called as curvilinear translation. Instead, if the points are moving along parallel straight lines, it is called as rectilinear translation. Okay, so these are the different type of motion: translation, rotation, and general plane motion. And under the translation, we have two type of translations. One is rectilinear translation, in which the particles will be moving along parallel straight lines. And the second one is curvilinear translation, in which the particles of a body will be moving along parallel curved paths. Okay, then this is called as curvilinear translation. If the curve is a circle, then it is called as rotation or angular motion. Okay, so in curvilinear translation, to specify the position of a particle, we need two coordinates. Okay, to specify the position of the particle at a particular instant, we need two coordinates. Okay, so let the coordinates be x equal to f1 of t and y equal to f2 of t, where x and y are dependent on time, or they are functions of time. Okay, so x is equal to a function of t, y is equal to another function of t. Okay, so these are the two coordinates, x and y, with respect to the origin. Then x is equal to f1 of t represents the position along the x-axis, and y is equal to f2 of t represents the position along the y-axis, or the motion, or these two shows the motion of the particle. You can see a figure here in which a particle is moving from origin along this path like this. You can see, and we are considering a particular point P here. Okay, its projection on the x-axis will give you this distance x, and on the y-axis will give you y. Okay, it is projected to x-axis, it is x, and the projected to y-axis, it is y. This is y. Okay, and this is x. This is x. Okay, so this is x and this is y. Here, let us consider the position of the point or body after a time of dt seconds, a very small time of dt seconds. Okay, let it be at this point, say p dash. Okay, so initially the point was at p, and after a time of dt seconds it moved to p dash, and the distance traveled is delta s, an infinitesimally small distance traveled is delta s, and its components along x and y directions are delta x and delta y. You can see here delta x and delta y. Okay. Now, if these are displacements, so delta s should be equal to delta x plus delta y, because these are vectors. Displacement is a vector quantity. Therefore, delta s equal to delta x plus delta y. That gives, if we divided this equation by delta t, delta s by delta t is equal to delta x by delta t plus delta y by delta t. Okay, delta x by delta t plus delta y by delta t. Then what is delta s by delta t when delta t tends to 0? When this tends to 0, it will be ds by dt. Okay, or ds by dt, that is derivative of displacement with respect to time, is velocity v. Okay, so from here we will get vx equal to dx by dt and vy is equal to dy by dt. So these are the components of velocities along x and y directions. Okay, so this particle is moving along a curvilinear path, or it is having a curvilinear motion. It is moving along a curved path, and the two components, instantaneous components of the velocity of the particle, is dx by dt and dy by dt, and the velocity can be represented as, or the resultant of the velocity, v is equal to vx plus vy, where all these terms are vectors. Okay, then the magnitude of this vector will be square root of vx square plus vy square, and the direction theta will be tan inverse vy by vx. Okay, tan inverse vy by vx. So this is theta. Okay, so this is vx and this will be vy. Therefore, tan theta is equal to vy by vx, or theta is equal to tan inverse vy by vx. Okay. Then, from equation 1, if we differentiate it with respect to time once again, what we will get? dv by dt is equal to dvx by dt plus dvy by dt. Okay. We know what is dv by dt, isn't it? dv by dt is acceleration, and dvx by dt will be acceleration in the direction of x-axis or along x-axis. Okay. Or we can say this is the x component, one component of the acceleration, and this is the second component, or the y component, that is dvy by dt, that is equal to ay. Okay, so therefore a is equal to ax plus ay. These are vectors. Vector I is equal to vector ax plus vector ay, or a is equal to ax plus ay, and the magnitude of the acceleration a is equal to square root of a square plus ay square, and its direction is theta is equal to tan inverse ay by x. Okay. So sometimes instead of this x and y components of acceleration, we may need to express them as normal and tangential components of acceleration. Normal and tangential components of acceleration. Okay. So they are represented as an and at. A suffix n and a suffix t. That is normal component of acceleration or normal acceleration. At is the tangential acceleration. Say, for example, if a body is moving along a curved path of radius r, then it will have a tangential acceleration like this, or tangential velocity, and obviously if the velocity is changing with respect to time, it will have a tangential component of acceleration, and it should have a normal component of acceleration also, like this. Okay, so the tangential component will be due to change in magnitude. change in magnitude, and the normal component will normally be due to the change in direction of the velocity, because in each and every point the direction of velocity will be changing. If we consider this as velocity, this will be the direction at this point. Say at this point this will be the direction, and if you consider this point, this will be the direction. Each and every point the direction will be changing, and this normal component will be due to the change in direction of the velocity, and this component, this tangential component, is due to the change in magnitude of velocity. I'm talking about the acceleration. Okay, so there will be two components of acceleration, one tangential component and one normal component. Okay, so these are termed as AN and AT. So this is AN and this is AT. Okay, so this is AN and this is AT. Okay, now let us see how we can derive this equation. Say for example, AT, A is equal to total acceleration, A is equal to AN plus AT in vector form, and A is equal to square root of AN square plus AT square. Consider the motion of a body along a curved path. See, this is the curved path along which a body is moving, and this is the velocity at this point, because this is the tangential velocity at this point, or this is the velocity at this point, say tangential to this path. Let us consider another path at an angular displacement of d theta after dt seconds. Okay, after dt seconds. So this is the point where we consider the velocity. So the velocity is found to be v plus dv. Okay, here it was v, and after dt seconds the velocity is changed or increased to v plus dv, or the change is dv in dt seconds. Okay, now let us consider the radius of the circular path is r. If this is O origin, this is r, and omega is the angular velocity at this point. Here the angular velocity is omega, here the angular velocity is omega plus d omega. That is a change in angular velocity is there, that is with a d omega. Okay, now we can represent this velocities, linear velocities v and v plus dv in a vector form like this. Okay, so if you represent it, this will be v and this will be v plus dv. This is parallel to v and this is parallel to v plus dv. Okay, this is parallel to this and this is parallel to this, v plus dv, and they definitely due to the geometry this will be d theta. This angle will be d theta, the same angle between these two. Okay, then let us construct one right angle triangle with this angle as 90 degree, that is OBC or OCB, with the angle C as right angle. Okay, then you can see V is only up to here, and V plus this will give you this one, or this is equal to this plus this, provided they are vectors. Okay, so these are vectors because they are velocities, therefore this plus this is equal to this one. Or another way we can say the change in velocity is AB. Is it not? The change in velocity is AB. That is why when we added this to this, we got V plus dV. Okay, we got V plus dV. When we added this much, we got V plus dV. Okay, so we can write AB equal to AC plus BC. If we consider these as vectors, AB, AC and CB as vectors, then AB, this vector is equal to AC plus BC, like this, AC plus BC or CB. Okay, So AB is equal to AC plus BC. Okay. And we can see these are components of AB. AC and BC are components of AB. Okay. Then here, if you divide this equation by dt, we will get AB by dt is equal to AC by dt plus BC by dt. Then AB by dt is the acceleration, that is change in velocity divided by time. Okay, change in velocity divided by time, that is equal to AT. AC by AT is the tangential acceleration AT, and BC by dt is the normal acceleration AN. Therefore, the total acceleration A is equal to AT plus AN, all are in vector form. Okay. Then let us derive this the expression for AT and AN. Okay. See, from the vector diagram, so this is the vector diagram. From the vector diagram, we can see what is AC. What is AC? AC is equal to OC minus AC. Is it not? OA. OC minus AC is equal to OC minus OA. OC minus OA, isn't it? AC is equal to OC minus OA. So that is OC is the cos component of V plus dV, because this is a right angle, this is 90 degree, it's a right angle triangle. Therefore, OC is cos component of V plus dV. Then its cos component will be OC. Okay, you can see here. So AC is equal to OC minus OA in vector form. AC by dt is equal to OC minus OA divided by dt, and AC by dt is equal to OC is V plus dV cos d theta. V plus dV cos d theta. Okay. Then minus V, that is OA. Okay. Divided by dt. Okay. Then this is AC by dt is AT, the tangential component of acceleration or tangential acceleration, that is equal to dV by dt. How it is coming as dV by dt? Because V and V into cos d theta. When theta is approaching 0 or tending to 0, cos theta will be 1. Therefore, V plus dV minus V will give you V plus dV minus V divided by dt, because this will become 1. Therefore, it will be V plus dV minus V divided by dt, then it will be dV by dt. Okay, it will be dV by dt. So, the tangential component of acceleration AT is equal to dV by dt, or it can be written as AT is equal to R alpha, where R is the radius of the curve, alpha is the angular acceleration. Alpha is the angular acceleration. Okay, so AT is equal to R alpha, or AT is equal to dV by dt. These are the expressions for tangential component of acceleration, or tangential acceleration of a body when it is traveling through a curved path. Okay, so it is equal to dV by dt, or it is equal to R alpha, where alpha is the angular acceleration. Alpha is equal to angular acceleration. Okay, Let us see how we can derive the expression for the normal components or normal acceleration. Okay. So that is denoted by an. It is equal to CB by AT that we have seen already. CB by AT here or BC by DT. CB by DT. AN is equal to CB by DT or BC by DT. So that is equal to what is CB from the vector diagram? CB is the sine component of V plus dV. This is CB. So sine component of V plus dV is V plus dV sine d theta. V plus dV sine d theta is this CB or BC. Okay. So V plus dV sine d theta by dt. That is AN is equal to V plus sine d theta plus dV sine d theta divided by dt. So we know when theta is very small, sine theta equal to theta. When theta is very small, sine theta equal to theta or sine d theta equal to d theta here in our case. So V sine d theta plus dV sine d theta divided by dt will give you V d theta plus dV d theta divided by dt. dV d theta divided by dt. Okay. Now we know dV is a very small term, d theta is another very small term. The product will be still very smaller, which can be ignored or neglected. So this term we can cancel out and we will be getting only V d theta by dt. V d theta divided by dt will be the remainder. Okay, the remaining term. So we can write it as AN is equal to V into d theta by dt. V into d theta by dt. But we know d theta by dt is omega. This is omega, the angular velocity, angular displacement per time, or change in angular displacement with respect to time, that is omega. So AN is equal to V into d theta by dt, that is equal to V into omega. V into omega. Then we know another expression, omega is equal to V by R. From where it is coming? V equal to R omega. V equal to R omega. So AN is equal to V into V by R, that is equal to V square by R. This V square by R. And also in another form also we can write this as AN is equal to R omega square by R omega square by R, because V is equal to R omega, substitute it here. So R omega the whole square divided by R is equal to R omega square. So the expression for AN, it is either V into omega or V square by R or R omega square. There are three expressions. Okay. So the component of acceleration tangential to the path AT, or the tangential acceleration, is R alpha, and the normal acceleration is either we can say V omega or V square by R or R omega square. Okay. So these are the components of acceleration in tangential and normal direction to the path, to the curved path along which a body is moving. Okay.